Check this out. It's the world's biggest parabola. Located in China, it's a single dish radio telescope, 500 meters in diameter. Not even ET could complain about coverage this good. Instead of phoning home, this behemoth listens for echoes from dwarf galaxies up to 3 billion light years away. Could this mega dish save us from an alien invasion or an apocalyptic asteroid? Maybe. Today, we are going to surf some invisible waves, all guided by the Hubble parabola. So, if you've ever wondered, where am I ever going to use this in the real world? That's exactly what we're unpacking. So what's up with the lab coat, you ask? Well, our journey today starts with a quick dive into a bit of physics before we return to the safety and simplicity of our maths world. Before we get started, let's recap the first two videos and activities. In the first session, we did some paper folding to create a beautiful U-shaped curve. With the help of TI Nspire, we modelled the curve with a parabola. In the second session, we proved the U-shaped paper folding curve is indeed a parabola and can be defined by a quadratic equation. We discussed the benefits of modelling, including the London skyscraper that isn't really parabolic, but can be modelled by a parabola, and therefore has some undesirable parabolic properties. In this session, we will see that light and sound can be modelled by waves. Then, we will use mathematics to see how these waves behave when they encounter a parabola. When an object vibrates, it creates a series of compressions and rarefactions. These can be modelled as waves. If these vibrations occur within a certain frequency range, we can hear them as sound. Oscillating electric and magnetic fields create an electromagnetic wave. Depending on their frequency, we may see that as visible light, or perhaps it could be infrared or ultraviolet light, or even radio waves or microwaves. To help imagine a wave, think of ripples in a pond. The further away from the source, the straighter those wavefronts appear. For our mathematical modelling, we will assume that the wavefronts occur as straight lines. Now, with the physics and assumptions out of the way, let's get back to the maths. Think of a wavefront as a series of points. If we plot these points on the Cartesian plane, we can give each and every one of them a set of coordinates and calculate their individual movements as they collide with the parabolic curve. As each point collides with the parabolic curve, it is reflected back through the focal point. To prove this, we would need some calculus, but we're going to leave that for the senior maths classes because real-world maths gets a little complicated. So let's continue with our calculations. I've defined a parabola y equals 0.05x squared. The focus of this parabola is at 0,5. Now, imagine a wavefront represented by the line y equals 8. We can choose a point P on that line, let's say 3, 8. How far is that point from the parabola? As P moves towards the parabola, its x-coordinate is not changing. So we can calculate where this point strikes the parabola by substituting in our x value. So y equals 0.05 times 3 squared, which gives us y equals 0.45. So point P will travel from a y value of 8 to a y value of 0.45, a vertical distance of 7.55 units. As point P is reflected back through the focal point, we can use Pythagoras' theorem, that is the distance formula, for the distance between these 2 points. we can substitute the values in and calculate the square root of 0 minus 3 all squared, that's the difference between the x values, plus 5 minus 0.45 all squared, the difference between the y values, giving us a distance of 5.45 units. So the total distance travelled by point P, a point on the wave at y equals 8, is 13 units. Now, pause the video and try a couple of other points on the line y equals 8. You might like to try -1,8 or 6,8 or even 0,8. And notice what happens. That's going to help you answer the rest of the worksheet. That's all for this video. And our thought for the day: if the space telephone rings, should we answer it?